We're team abnormally distributed, and I'm Prajwal Kiran Kumar.
Hi, this is Rasya Ramesh.
Hi, I'm Rahul.
Our problem statement is to predict movie revenue based on attributes like movie budget, popularity index, vote count, etc. We have also implemented keyword analysis to provide weights to predict revenue. We have built two recommendation systems, one to predict ratings for a movie by a particular user, another to predict movies similar to a particular movie.
Our dataset is derived from the TMDB dataset API, which was neatly filtered, segregated, and available on Kaggle. It had four main CSVs, namely movie metadata, consists of movie titles with summaries of vote counts, averages, revenues, budgets, etc. Pre-processing metadata includes imputed values for revenue and budget fields using k-nearest neighbors regressor for better accuracy. Keywords consists of keywords and associated IDs, which is derived from movie taglines and overview, among others. The keywords were replaced with most occurring synonym and lemmatized. Frequencies were calculated and used for further analytics. Other CSVs were ratings and credits, which didn't need any pre-processing.
Our process involved three stages. Firstly, collecting and pre-processing the data, which was previously explained in detail. This is followed by multiple linear regression, and finally, building the recommendation system. The first step resulted in our literature survey report and the completely pre-processed data that we have used in the further analytics. Second step was used to build a model. And finally, we also performed keyword analysis on the model to give weights for the keywords. This was followed by building a complete recommendation system of two types, content based and collaborative filtering. Now, let us go over these steps in detail. Firstly, we used k-means clustering algorithm to cluster the movies. The elbow point for this algorithm turned out to be 4, resulting in 4 clusters for the movies. In particular, let me highlight the one in orange. This cluster consisted of just 97 movies, and it is representative of all the hit movies. This is because it is the cluster with the least number of movies, but with the maximum budget, maximum revenue, maximum runtime, maximum vote average, and also maximum number of votes. This goes to show that the number of movies which are successful in the box office are very less compared to the number of movies that have very average revenue and other such parameters. This is particularly shown by the cluster numbered 0. When the same variables are used in the regression model, the resulting R squared and RMSE values were not significant and the regression model needed tweaking a little bit. We engineered a new feature which was the product of the vote count to the power of a fraction multiplied by the vote average. Considering only vote count as a feature would not be representative as it would not show the ratings of the movie. Considering only vote average is also wrong because very few people could have voted a very high value and that would give a very large average. Hence, we considered the product of the vote average and the power of the vote count to a fraction, which will not only account for the ratings of the movie but also decrease the weightage of high rating if too few people have voted for the movie. This metric, when used in the regression model, gave satisfactory results in our predictions.
We have attempted to build a model using weighted means. The keywords are assigned weights which are calculated using the revenues of movies. Each keyword has a weight equal to the average of the revenue of all the movies which they have appeared in, and the movie revenue is further predicted using the average of the keyword weights. The revenue depicted on the screen indicates the weights for some individual keywords. The prediction on the right is indicative of the log of the actual revenues. The log transform is done for range transformation.
We have implemented content-based filtering and collaborative filtering. Let us begin with content-based filtering. Our first recommendation engine involves the usage of the overview column of movies metadata. All strings are initially vectorized. We obtain the cosine similarity matrix of these strings. Now, if we are given a movie, all we have to do is get the row of the matrix corresponding to that movie and take the columns with the highest cosine similarity in that row. This way, a list of recommendations is obtained. Our second content-based filtering engine works in a similar way, except that it uses keywords, cast, crew, and genres. After pre-processing the columns, a soup of words is created by combining all of them. This long string of actors, directors, keywords, and genres of the movies that we feed into the vectorizer is just like the overview in the previous engine. After that, we obtain the cosine similarity matrix the same way, and the following steps are identical. Our final recommendation engine was made using collaborative filtering. We use the engine to predict how a user will rate a particular movie. We adopted single value decomposition algorithm. The dimension of user item matrix, which is sparse, is reduced. It helps us better understand the relationship between users and items as they become directly comparable. We get an average RMSE of about 0.89.
Our recommendations were satisfactory, and the RMSE for various models were as follows. Future work for this project includes building a dataset through web scraping of reliable data, using time series to model the data to account for inflation, build genre-based classifiers, and implement regression on individual clusters for better interpretation.